Thousands of years ago, ancient navigators crossed thousands of miles of open ocean with a success rate exceeding 85%. This was not a product of luck, it was the result of a rigorous, applied spherical geometry. In this century, we recognize that these mariners functioned as human calculators. They treated the sky as a living, rotating map, a geometry puzzle where the variables were stars and the horizon was the axis of survival. The secrets to surviving the high seas were written not in sand or ink, but in the rotating geometry of the firmament above. At the equator, a tiny error of just 1 degree in latitude translates to roughly 60 nautical miles. In the vast expanse of the open ocean, that distance is the difference between reaching your destination and drifting into oblivion. This lethal constraint forced ancient navigators to develop rigorous, repeatable mathematical systems. They treated the stars not as lore, but as survival tools, calculating their position with an accuracy that determined life or death. The zenith star is the key to ancient navigation. Every star has a declination, a specific point on Earth where it appears directly overhead. If a navigator knows that a specific star, like Arcturus, passes through the zenith of their home island, they can use it as a latitude anchor. The navigator sails north or south until the star is directly overhead. When the star hits the zenith, the ship has reached the exact latitude of the destination. By pinning the star to the zenith, navigators transformed the vast, featureless ocean into a manageable geometric puzzle. Ancient navigators utilized a simple tool called a gnomon, a vertical rod that acted as a precision shadow clock. At local noon, the shadow cast by the gnomon reaches its shortest length, directly mapping the sun's meridian altitude. By measuring this shadow length, mariners derived the sun's angle relative to the horizon. This angle serves as a fundamental geometric coordinate. By comparing this observed altitude to the known daily solar declination, navigators could calculate their latitude with high accuracy. This method provided a reliable backup for spatial awareness, ensuring a consistent coordinate system even when cloud cover obscured the stars at night. Solar shadow geometry effectively bridged the gap between celestial observation and terrestrial location, a testament to ancient mathematical ingenuity. Polynesian navigators mastered the ocean by mapping the horizon into 32 distinct houses. Each house represents the specific azimuth where a star rises or sets. By memorizing the rising and setting points of hundreds of stars, navigators created a mental star path. They did not need physical tools. They kept a precise heading by observing which star occupied which house. This sophisticated mental compass allowed them to maintain a heading across thousands of miles of ocean with an incredibly small margin of error of just 1 to 2 degrees. Ancient navigation was not based on static maps, but on dynamic mental trigonometry. Explorers calculated their latitude and longitude through complex stellar projections in their minds. These ephemeral mental calculations were later transcribed into physical cartography. Ancient maps were the final static output of high-speed, live oceanic data processing. This proves ancient maps were never just rough sketches. They were scientific records of rigorous mathematical discipline maintained under the most extreme conditions. Today, we look at the modern legacy of wayfinding. Research into ethnonavigation reveals how ancient techniques allow the human brain to process complex spatial mapping without any digital mediation. By studying these star path methods, we understand that our ancestors utilized a standardized mathematical framework, allowing them to navigate the vast ocean with precision. This proves that sophisticated, standardized mathematical logic was the foundation of human expansion, long before the invention of modern sensors.